Critical numbers, Fermat's theorem, the extreme value theorem. Oh, the percentage is such a confusing thing, but the truth is, it's not. This is one of the simplest things you're going to learn because we've done so many derivatives already. We've done hard math, but now you have to apply them. So let's say that I have a weird function that goes maybe like this. Okay, the critical number is any time you see a directional change like this. Of course, this is going up and then going down, and then down, and then up, and then down, and then kind of up, and then kind of down. You get that. You don't need my help seeing up and down. Critical numbers are that moment, let's use a color, let's use this color, where those things change. And I'm sure you can spot almost all of them right away. The eye is fantastic at that. And we use what's called a closed interval because maybe we only want to look at, say, this to this. I mean, you could look at everything in the universe, but you'd never be able to solve anything. So maybe we're only looking at this particular window of a function. And they want to find what they call absolute and local maximums and minimums. Everything where you see a yellow dot is a local maximum or minimum. That's pretty simple. It's local because you can draw a boundary around it, and it's still going to be the biggest or smallest one in the area. That's what makes it local. But while we're looking in this large universe, no matter how far and wide I set this, the global maxima or minima, this might be the minimum, but if I make it this as the window closed interval we're looking at, then this guy's going to be my global minima. And this guy's just only a local minima. This guy is a global and local minimum. Okay, so global maximum, local maximum, local maximum. If I change the closed interval, if I only look at this group, well, global maximum is this guy now, or extreme maximum, depending on who you talk to. That's the extreme theorem, value theorem. That's all that critical numbers are about. They're about finding these moments. And wouldn't you know it, every critical number has a slope of 0. It's required. That's what Fermat's theorem says to us. They have a slope of 0. So, expanding on that, Fermat was like, okay, if you take a closed interval like this, and you find all the critical numbers, like this, you find them by saying where f prime of x equals 0. And wherever you find that, that's here, that's here, that's here. One of those is going to be your absolute maximum or minimum. It's here, here. So that's the entirety of the lesson for this calculus explainer. It really is that simple. So anytime you're asked to find an extreme value, a global value, a local value for a maximum or minimum, what you're going to have is a slope of 0. On some closed interval, maybe you call it a, b, or something like that for your x values. Who cares? Who cares? All you need to remember is that every maximum or minimum has a critical number, which is what we refer to as when the derivative is equal to 0. It has a slope of 0. Did I say slope of 0 enough yet? So now you understand global maximum, global minimum, local maximum and minimum, critical numbers, extreme values, they all refer to the same phenomenon. If a global maximum exists, you find it this way. So let's take an example real quick. Let's just pick something real like y equals x cubed. I'm sure you know by heart that x cubed looks kind of like this. I've made it a little more extreme. And the first thing you do is say, okay, what's y prime? Y prime equals 3x squared. Fantastic. Set it to 0. 0 equals 3x squared. I'm sure you can solve for x. X is equal to 0. That's at this moment here. So this is one potential local and global maximum or minimum. So if I choose a boundary, let's say this, and over here, you check the edges. So maybe here I chose x is 1, and of course here x equals 0. Let's say over here I chose x equals -2. If I look at the values here, I'll find that x equals -2 is going to be my global minimum, and x equals 1 is going to be my global maximum, just based on the values I chose for x. But always check wherever the slope is equal to 0, because the function you have may go like this, or it may go like this. You don't know without checking those values. But what this theorem does is it allows you to say, I only need to check the boundaries, the edge here and the edge here, and where my critical numbers exist. So just to hammer it home, if I have something like sine of x, I take the derivative, you get cosine of x. Set it to 0. And you may not remember from trigonometry, but if that's the case, you're in deep trouble. Cosine is 0 when the x value is 0. So that's here, and that's here. That's at pi over 2 and 3 pi over 2. So you should expect on sine, when you see a slope of 0 here, you can bet that's at pi over 2, because that's when cosine is equal to 0. And that is going to be a local maximum. 3 pi over 2, what are you going to get here? A local minimum. Now this is also the global minimum, and if I move this over just a little bit, this is now the global maximum as well. So you see what happens? These critical numbers just tell you where to look. But what if I change the interval on which I'm looking at sine? What if I took this and this? Well, the boundaries are going to be what gives you this. And what I'll find is that there is no place here where cosine of any of these x values is equal to 0. It always has some kind of a negative slope here. So always check the boundary x value, and they'll tell you like a equals, I don't know, 0 or something, and a equals 2, whatever random thing. I'm just choosing randomly here. And whatever critical numbers you can find. In this case, there aren't any, because there's no slopes of 0. So just always, 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 as you're going through this lesson, we'll do a couple of the problems. Check the boundaries and check the critical number, which is whenever you get a local maximum or minimum by finding a slope of 0. Did I hammer it in enough yet with the 0 slope? That's everything with this whole critical numbers nonsense. Let's just move out of the explainer and go do some problems.